All right, jump straight into it. Spatio-temporal species distribution models, and I'll try not to trip over the chairs while I'm here. All right, core research aim is to detect species response to climate change using dynamic predictors and anomalies from their mean values. So before we get into that, let's talk about why we should even care about time in the first place, and what do we mean by anomalies. All right, so ecologists tend to use these 30-year data sets that are available for free, and the problem with these is that they mask the accelerating changes that have happened in the climate, particularly since about 1990. All right, so it's quite difficult to get predictors at the relevant spatio-temporal scales as well. Right, the common sources are these BioClim raster datasets, WorldClim, CHELSA. Anyone who works in this area is kind of familiar with this stuff. But as I said, these are these fixed temporal windows, and they're averaged over these fixed 30-year time periods. Other issues include the staleness of the data sets. So as soon as you've got them, they're out of date. So people are doing a lot of studies using these anyway, even though their observation data doesn't even fall into this time window. The choice of variable and resolution mismatch between the data that you have and the climate data that you can get hold of. And if you come from a computer science background like me, big problem is these manual downloads, right? So there's very few access to APIs. And you might think, oh, I don't care, I just want to do my study. The problem is integrating this into some sort of repeatable workflow for data governance. And so we don't have this reproducibility problem. So that's no good. All right, so overall, look, it's a technical challenge. It requires ecologists to really have to jump through a lot of hoops just to do basic stuff. But here's the problem. If we want to find species response to climate change while simultaneously treating the climate as temporally static, well, that's not going to work, right? So we've got to make a change here. All right, now let's talk about anomalies. So we want covariates that capture long-term climatic changes. So let's do a little bit of maths here. Everyone else did lots of maths, and I should probably put something up here. So I thought that's pretty good. Right, so we've got temporal means at all the locations across a particular area, and we want to look at how much that mean in a given year is different from the overall mean over your whole study temporal window. And this is borrowed straight out of climatology. So when we plot them, this is a random sample of 10,000 spatial locations in the study area that I'll introduce you to shortly. You can see these anomalies are, as we all know, we're getting more and more extreme temperature events as time goes on. So that's pretty grim, but it's no surprise to anyone here. All right, so vertical axis here, you can think of increasing temperature anomalies as a proxy for time moving forward. So let's fix that and let's have a look. What are we talking about here? We've got temperature along the bottom, and we've got those anomalies coming up vertically. What do we think? So we talked about, okay, that's time. How are these things going to interact? Well, what we see is as we get more and more extreme temperature events, what we're expecting to see is species responding by moving into colder habitats. The interaction surface between those two things would look something like this, some sort of negative interaction surface. And obviously we would, if we fit models, we want to see this coefficient being negative, and that's what we're talking about here. And that's an example of one of an actual one of the results of our models. This is I think it's the snow gum down in the Snowy Mountains region. And we've just overlaid that with the actual observation data that we have, just to give you an idea that we are actually seeing this in some of the species that we've captured. All right, so that's all very well and good. This is great, it's all interesting, but what species are we going to look at and where are we going to look? All right, so look, alpine summits, these form a natural laboratory for doing climate change research on species because by definition, they control the population pressures and land use, right? So you're not worried about people building houses and all this sort of stuff in here. So species under stress can migrate to higher elevations, at least until they run out of world, then they're sort of stuck. And then or into habitats that were previously too cold. So that's our sort of hypothesis. All right, Snowy Mountains region. This is what we're looking at. Just over 85,000 square kilometres and a 46-year temporal window. So this is a big problem in space and time. Snowy Mountains region. This is the official Australian Alps here. If you can see that, how's that come up? That's come up terribly. That is the digital elevation model for the Snowy Mountain region. But everyone here knows our area, so that's okay. Moving up here to the northeast is where we get increasing elevations. So what we expect to see is this sort of thing. We put a buffer around that just so that we can try and control for what's going on in the immediate surrounding regions. So this particular case is our 50 kilometre buffer in that case there. All right, so that's good. Now we know what we're looking at. Now we've got to build some species data sets. And I know there's lots of Sams here today, but Sam was talking about how, using iNaturalist. We've gone a slightly different path. We're trying to use systematic surveys here, which is much harder to do. It turns out to be really hard to do that. There's many of these, many formats, and you often have to infer the absences yourself. Very often the counts are there, or it's a zero count, or there's just no records there. So there's a lot of data engineering, and this is, as anyone probably knows, this is where real data science comes in. You spend all your time jumping through these hoops. So we want to try and fix it to native species, temporal window of about 30 years, and we want a median elevation of about 1,000 meters so that we know we're up in this region here. When we did that, originally we started with, got about 5,000 different species data sets. We applied these filters that we put on here, and we got roughly 80 candidate species, and you can see with a variety of different presence observations in there. Okay, almost there. Climate variables. So now we've got our species, we know where we're looking, we've got to go get climate information. So we spoke to the climatologists at UNSW, and we're informed that this ERA 5 comes out of the Copernicus project from the European Centre for Medium Range Weather Forecasting. This data is the best of breed. So that's what we started with. There's 80 variables there, precipitation, etc. At hourly resolutions going back to 1950. They've got a nice API around there. There's a Python library you can use, and there's an R package around that, so you can pull this data in. That speaks to that repeatability I was talking about before. And so now the question becomes, what do we choose rather than what can we get, which is traditionally how it's been in ecology. All right. Even when we get them, though, we get these 9 kilometre cell resolutions, so we've got to downscale these to be useful. And to do that, you've got to apply the relevant physics. In this case, as an example, if we use topography for temperature and get these down low. So we did a variety of different, I'm not going to go into that right now, but we tried various different situations to work out how to use kriging to downscale this raster data properly. A bunch of different scenarios. All you care about here is this bottom one here, elevation and slope. You'll probably guess that out of the gate, but still that we wanted to back it up by our data. All right, almost at the home stretch. Modeling in space and time. What do we got? All right, so we've got a binomial response with a complementary log-log link. We've got our space-time variables implied via the space-time climate covariates, and we've got that anomaly interactions, what we're looking for, and non-linear terms in there as well on these things, because we want to try and capture that non-linear species response to any extremes. So we look at our main effects. So we look at aspect. We're up in the mountains here. Which way are they facing? You get very different north and south. So this, what they sometimes call northernness and easternness, bit of a mouthful, but that's what they are. We have soil moisture, those temperature coefficient, those temperature variables. That interaction term in red is what we care about the most, those non-linear terms, and then a general spatio-temporal smooth to wrap it all up, try and mop up any correlation that we haven't already modeled. That smoother is made up of a tensor product of 2 bases. That's a Gaussian process over our eastings and northings, and we also have a cubic regression spline for time. We use eastings and northings because our uncertainty and our altitude are also in meters. I know people love to use latitudes and longitudes, but we want to have this for interpretability, all using the same units. So when we do that, we get a whole bunch of this, just a random selection across these things. You can see we saw some of these are what we're looking for. Some of these are like a saddle point. So, and that, look, that makes sense. We didn't start with going, we think this species will do something. We looked at all the data we had and said, what's going on? Right? So we don't expect to see everything the same here. So these results here, when we put a regression mod, just remember that's what we're looking for. We're looking for this sort of negative interaction down the bottom here. We ran a meta-analysis over the whole cohort of species here. And this is just to point out that we don't really know what's going on if it's happening on this side here. And what we can see here is a nice clean, you see most of these species are on this negative side here, and down the bottom here, and overall for the whole cohort, we've got quite a strong, significant response there. And this would be a great place to just leave it, and I could go and sit down and go excellent and take questions and all that sort of thing. But this world we live in likes to play tricks with PhD students, and all is not as good as it looks there. So what we did, we got more data, and this comes from New South Wales Bionet and from the Victorian Biodiversity Atlas. They update their data regularly. We pulled all that in. We got quite a lot more data in here, ran the same models, and we saw things slightly different, changed quite a bit. You can see this is about roughly half a negative, and of them, roughly half are significant. The ones in red are the significant ones, right? So we're pretty excited we've got something by the tail. When we put all this in now, we get over here, we go, ooh, ugh. Right, so this is the more recent data. That looks much more drastic than it is, but I'll remind you, in this case, we've got 165 species up here, whereas in the previous slide, we only had 80. Okay, so in here, the response rate here is only about 5%. And as you can see here, the overall for the cohort has moved from being negative across to being positive. All right, so not an exciting outcome given all the work that we've done so far. It doesn't mean that we've got things wrong. It just means we need to go deeper into this and actually work out where we go from here next, because some of these species very clearly still are responding to climate change. The only difference here is that the cohort as a whole isn't acting the way we thought that they might. All right, so where do we go from here? All right, so next things to look at is this robustness of results. It's very, very sensitive to the way we generate absences is a bit of a problem. We need to dig deeper into that. Really want to look at quantification of changes. So what you've got here is an example where we look at what our predictions for a particular species look like at date 1 and date 2 and how the difference of them, how are those predictions gradients done, and we want to see like what direction, what might we expect to see these things shift as we go forward. And lastly, we keep putting this on the back burner, but we've got some really good ideas for a interactive visual model for ecological data sets. So they're all the stuff, and thanks to everyone at DARE for supporting us all through this as well. That's it. Thanks.